All right. In the next part of today's lecture, we're going to talk about weight initialization. Now, the theme in our discussion of weight initialization will be very similar to the theme when we talked about normalization. The main thing we're going to be going for in choosing our initialization scheme is to ensure that the gradients in the network look reasonable by ensuring that the activations are on roughly the same scale. So we want the overall scale of activations in the network not to get too big or too small as we increase the number of layers. And this is important so that the gradients propagate well through the network. So we'll talk about some basic initialization methods, which are going to ensure that the activations are on a reasonable scale, and that the scale of the activations, crucially, doesn't grow or shrink as our network gets deeper, as we increase the number of layers. We'll then talk about some more advanced initialization methods, and these more advanced methods try to actually more explicitly reason about how well behaved the gradients of the network are. And the way that the reasoning there is going to go will be pretty similar to our discussion of residual networks in the previous lecture. Just as a reminder, we can write out the derivative of the loss with respect to the weights at a particular layer as a product of many, many Jacobians, specifically the Jacobians of all the functions between that layer and the loss. Now, we don't really care so much at this point about what those Jacobians are. We can just say that they're a bunch of matrices, so J1 through Jn, and we're multiplying them all together. And as we discussed in the previous lecture, if we multiply many, many numbers together, if those numbers tend to be less than 1, then their product will be close to 0. If they tend to be greater than 1, then their product will go to infinity. But if they're all about 1, then we get a solution that's about 1. Now that's for scalar values. For matrices, this means having their eigenvalues be close to 1. So the more advanced methods we'll discuss will basically try to initialize the network so that these Jacobians have eigenvalues close to 1. But first, we'll talk about the basic initialization methods, and those are just going to try to keep the magnitude of the activations about the same at all the layers. And this is actually good enough in most cases. So if we had a genie that could basically give us any initialization we want, we would just ask the genie to initialize us right at the global optimum. That's kind of the best thing we could possibly hope for. But of course, we have no idea where the global optimum is. We don't have such a genie. So in the absence of that, we're not going to try to initialize our weights so that they're close to a good solution. We're just going to try to initialize them so that at initialization, the derivatives of the neural network are of high quality, meaning they actually point in a direction of an optimum. Essentially, we just want to avoid initializing our network close to a plateau or saddle point, because that's going to make it really hard right at the start. Now, one very simple choice, and this choice works well for very small networks, but it quickly becomes impractical as the networks get bigger, is to initialize the weights to some small random numbers. For example, we could pick a normal distribution with a mean of 0 and a standard deviation of 0.0001 or something, right? You don't want to initialize the weights to be exactly 0 because then the gradients will all be 0. But if you initialize it to a small random number, for small networks that'll actually work. The problem is that as your network gets deeper, this will quickly give you bad answers. Because imagine that your inputs are roughly on the scale of 1. Right? You multiply them by a bunch of weights with a standard deviation of 0.0001, and you'll get a bunch of numbers that are on the order of 0.0001. Then you get some nonlinearity. The nonlinearity is probably going to keep them at about that same scale. And then you go into the next layer, and now it's going to multiply them by 0.0001 roughly. So then you'll end up with 0.00000001, and so on and so on. So you'll have exponential decay in the magnitude of your activations. This experiment shows an initialization for a 10-layer network, and the plot in blue shows the mean on the vertical axis, and on the horizontal axis is the layer. So this is not a learning curve. This is actually each point corresponds to the mean of the activations at each layer. So you can see at layer 0, the mean is far from 0 because maybe the inputs are, here they tend to be mostly negative, but the mean quickly goes to 0. That's fine. We don't really worry about that. But the red curve is a bigger problem. The red curve, the y-axis, is the standard deviation of the activations at that layer, and the horizontal axis is the number of the layer. And you can see that the input has standard deviations of around 0.21 or so, and then as we go up in the layers, the standard deviation just tanks. It just drops like a stone to near 0. And the plots at the bottom, each plot corresponds to a histogram of a different layer of the activations. So you can see that the first layer has a healthy-looking histogram with a variety of different activation values, but as you get to layers 4, 5, 6, 7, 8, 9, and 10, there's virtually no variability in the activations. Essentially, the activations have all become 0. Now, why are we concerned about this? Why is this bad? Well, this is bad because if you recall the formula for the derivative of one of these linear layers, it's going to be delta times the activations of that layer transpose. So if the activations are 0, then the gradients are 0. And if the gradients are 0, then you're not making any progress. We learned about this when we talked about optimizers. We learned what kind of geographical feature in our optimization landscape this corresponds to. What geographical feature is it? Well, it's a plateau. In fact, it's a really bad plateau. So we would very much like to avoid initializing our networks in this way, because when we do this, we're basically initializing our network in the worst place we could possibly put it, in the middle of a really big plateau. Okay, so here's how we could think about devising a better initialization scheme. Let's say that we'll initialize our weights at some linear layer. This is going to be the case for any linear layer in the network. Let's call it W. And we'll initialize so that Wij, the ijth entry in the weight matrix, is sampled according to a Gaussian distribution with a mean of 0 and some variance sigma w squared. So the thing that we're going to try to figure out is what we should set sigma w to be. Now, we don't have to use Gaussian initializations, but this tends to be pretty simple. And it's actually enough for us to work out a pretty decent initialization scheme. So we could do something fancier than a Gaussian. The Gaussian turns out to be good enough as long as you choose its variance appropriately. The biases will initialize to just 0, and that turns out to be okay. So one question we could ask is, given a value of sigma w, what is roughly the magnitude of the values we get after this linear layer? What is roughly the magnitude of the z's? So here's the formula for every entry in z. So the ith entry in z, zi, is given by a sum over all the entries in A over j of wij times aj plus bi. Right? So this is just the formula for one of these linear layers written without matrix notation just to keep things simple. And I said that the biases will be initialized to around 0, so this term basically doesn't matter. And let's assume that the activations at the previous layer are themselves roughly Gaussian with a mean of about 0 and a variance of sigma a. And this is a reasonable choice. In fact, if we standardize x's, then we can kind of roughly say that x is going to come from a 0 mean unit variance Gaussian. I mean, it doesn't have to be, like x doesn't actually have to be Gaussian, but it will have a mean of 0 and a variance of 1, and that's okay. So it's kind of a sensible, if crude, model of what's going on. So then the question that we could ask is, everything here is 0 mean. Roughly, what will be the magnitude of these z's? Well, if the means are all 0, then the magnitude of the z's is basically the square root of their variance, right? Basically, what we're asking when we ask what's the magnitude of z's is what will be their standard deviation. Okay? So the formula I have here is for variance. Standard deviation is just the square root of that. If we write out the variance of z, since z is 0 mean, that's just the expected value of z squared. And you take this sum and you square it and you take its expected value, and then you will get each of the terms in the sum squared, and then you'll get a bunch of these cross terms. But the cross terms are going to cancel off because the means are all 0. So it's only the quadratic terms that will remain. So if everything is 0 mean, then the variance of z is just going to be the sum over all the dimensions of A of the variance of wij times the variance of aj. And we know that wij is going to have a variance of sigma w squared, and aj is going to have a variance of sigma a squared, and we're summing together a bunch of these things. So this sum is just going to be dA, which is the dimensionality of A, times sigma w squared times sigma a squared, right? Because we're summing over j a bunch of sigma w squared times sigma a squared, and how many things are we summing? Well, we're summing dA things. So that means that the variance of each entry in Z will be roughly dA sigma w squared sigma a squared. Okay, now we got on this track because we were worried that our choice of initialization for the weights will either increase or decrease the magnitude of the activations. And if the previous layer has activations with a variance of sigma a squared, and the next layer is going to have activations of magnitude dA sigma w squared times sigma a squared, then we know that if dA sigma w squared is greater than 1, the magnitudes will grow with each layer. If they are less than 1, then they will shrink with each layer. So if we want the magnitude of the activations to stay about the same layer after layer, we need to somehow make sure that dA times sigma w squared is about 1. So one thing we could do is we could choose sigma w squared to be 1 over dA. Or, equivalently, choose the standard deviation of the weights to be 1 over the square root of dA. So this is the basic principle is where we just need the standard deviation to be 1 over the square root of the dimensionality of the incoming vector. And this is sometimes called Xavier initialization. And it actually tends to work pretty well. So this is a similar kind of plot to what we had before, where we, this was produced by Andrei Karpathy, where now instead of initializing all the weights to small random numbers, we initialize them with a standard deviation of 1 over the square root of the incoming dimensionality. And you can see here that the standard deviation, the plot in red, is decreasing as the layers go up, but much less quickly. So somehow we haven't fully stabilized it. We're still seeing that the activation magnitudes go down, even though seemingly we did everything right. But it is going down a lot less. So for a moderately deep network, this would actually work just fine, and it's actually very widely used in practice. As a question here, why is the standard deviation still going down? Take a moment to think about why this might still be happening. So there's a little detail that we missed. We forgot about nonlinearities. See, after we apply this linear layer, we're going to then apply some nonlinear function to the z's, and that nonlinear function will change their magnitudes. One very commonly used nonlinear function is the rectified linear unit. Deeper networks will almost always use ReLUs because they're much better behaved than sigmoids. The problem is that the ReLU will zero out many of our activations. In fact, if our activations are really normally distributed, which they often aren't, but if they were, and they really had zero mean, how many activations would the ReLU zero out on average? Well, you would expect that if the numbers are normally distributed and zero mean, then about half of them will be negative. And if half of them will be negative, that means that roughly half of our activations will be removed. They'll be set to 0. And this will decrease our variance, right? If you have a variance of, sigma z, and then you zero out half the numbers, those numbers that you've zeroed out, they all have 0 variance. So now you have a bunch of numbers with 0 variance, a bunch of other numbers with the original variance, so their overall variance will be lower. The variance will in fact be cut in half. This might not seem like much, but it does add up. So here's that plot. This is for a deeper network. This is showing, again, standard deviation. You can see that the histogram of weights at the bottom does get pretty peaked at 0. Not nearly as quick as with the tiny numbers, but it still gets peaked at 0. All right, so here's how we could address it. Recognizing that about half of the numbers get zeroed out, what we can simply do is we can make the variance 2 times bigger, or equivalently make the standard deviation square root of 2 times bigger. So that means that instead of setting it to be 1 over the square root of dA, we set it to be 1 over the square root of 1/2 of dA. This is actually proposed in the ResNet paper, and while the factor of 1/2 might not seem like much, it really adds up when you have like 150 layers or more. So for these residual networks, that actually did end up making a pretty big difference. So here is basically the same plot as before, except now with this 1/2 factor, and now you can see that the standard deviations are basically staying in the same range. So you can see the printout at the top, they start off at 0.82 and they end up at 0.84. They're basically maintaining their magnitude. So as long as you put that 1/2 in there, it'll actually be pretty good. All right, Now, an even smaller detail, biases. So before we said that we'll initialize all these bias vectors to be about 0. But again, the ReLU causes a little bit of a problem for that, because if we initialize our biases around 0, then about half of our units on average will be dead. So oftentimes, especially when people don't use that 1/2 factor, it's actually pretty common to initialize the biases to some small positive constant like 0.1, because dead units, units that have where the ReLU has forced them to 0, also have gradients of 0. So while you could put the 1/2 in, and that will prevent the activation magnitudes from dropping, those zeroed out gradients can be a problem, and some people think that this prevents networks from training properly. So an alternative is to avoid having too many of these negative things and just add a small positive constant to the biases. And that also tends to be a pretty good idea. I don't think it's common to use both of them together, and it kind of seems like they might not work well together, because if you add the biases, then you won't have half the things getting zeroed out. But it's pretty common to use the small positive bias. All right, so that's kind of basic initialization, and chances are for most of the networks that you're going to train, especially if they're feed-forward kind of convolutional or fully connected networks, Xavier initialization will probably be a pretty good choice. However, one thing I do want to discuss, partly because it sometimes works well, and partly because I think it helps us understand what's going on with network initialization, is some more advanced initialization techniques based on orthogonal matrices. So, as I mentioned before, the derivative of the loss with respect to the weights at some layer is given by a product of lots and lots of matrices, specifically all of the Jacobian matrices between that layer and the loss. So without worrying what those matrices are, we can just write it as a big product of J1 through Jn. And remember that if you multiply lots of stuff together, if all that stuff is less than 1, the product will be about 0. If it's greater than 1, it'll be about infinity. So you only get a reasonable answer if all of these Jacobians are close to 1. And what does it mean for a matrix to be close to 1? Well, it means that its eigenvalues are close to 1. Now let's dig into this a little bit more. For every one of these Jacobians, for any matrix really, you can write it as a product of 3 matrices, U times lambda times V, for example by using singular value decomposition, where U and V are scale-preserving transformations. They're basically orthonormal bases. That means that the matrix U and the matrix V, when you multiply a vector by it, will not change that vector's length, it'll just rotate it in various ways. So these are orthonormal. Lambda is diagonal, and the diagonal entries of lambda are the eigenvalues of J. For non-square matrices, you can still do this. Now, talking about eigenvalues doesn't make as much sense there, but they're referred to as singular values. So, roughly speaking, lambda captures all the rescaling that this matrix does, and U and V capture all the rotations. So you can think of this visually. If your initial activation is a vector that looks like this, then U rotates it without making it longer or shorter. Lambda scales its dimensions without rotating it. So you can think of lambda as basically just applying a different scale to every dimension. And then V rotates it again. So U and V don't make the vector longer or shorter, they just rotate it. Lambda scales it. So if we can just get rid of this lambda, if we can basically force it to have scales of 1 along each dimension, that would be enough to ensure that this big product of Jacobians doesn't yield huge or tiny numbers. Now, of course, we don't set the Jacobians directly. What we choose when we initialize the weights is the weight matrices. But remember that the Jacobian for a linear layer is just the transpose of its weight matrix. So if we want to have these Jacobians have eigenvalues around 1, what we have to do is we have to take our weight matrices, perform something like singular value decomposition on them, and then somehow force that lambda to be a matrix with 1s on the diagonal, to be the identity matrix. So if we can just force lambda to be the identity matrix, then we'll have eigenvalues of 1 for our W's, which means that we'll have eigenvalues of 1 for the corresponding Jacobians, and everything will be good. One way we could do this is we could take some arbitrary initialization, run singular value decomposition on it, force the diagonal to be identity, and then put it back together. Now, of course, forcing the diagonal to be identity just means discarding that. So you basically run singular value decomposition, get u, lambda, and v, and then put it back together, but omit the lambda. So pull out u, lambda, v, and then just construct the final matrix as u times v. There's actually an even simpler way to do it, and this is actually some code from an actual implementation of an orthogonal initialization. So on the first line, it just constructs some kind of random matrix. And it doesn't even really matter all that much how you construct it. So in this case, it's just constructing a matrix where every entry is normally distributed with a mean of 0 and a variance of just 1. It doesn't matter what that variance is because we're going to rescale the whole thing afterwards anyway. Then it runs SVD, singular value decomposition. And singular value decomposition returns 3 matrices, u, lambda, and v, where u and v are guaranteed to be orthonormal and lambda is diagonal. And here lambda is not even used because we're just going to throw it in the garbage. And then what they do on the last line is instead of actually multiplying u and v back together, they just select one of the two, specifically the one with the right shape. Because if you want a matrix that's not square, then u and v will actually have different dimensionalities, and depending on whether the input or the output dimension is bigger, that'll actually change whether u or v has the right dimensionality. So you just pick whichever one has the right dimensionality. They're both orthonormal, so they're both good to use. So this is one way to get an orthogonal initialization, and this would keep the Jacobians well behaved. Now, this is a little bit more complex. It also doesn't account for all this stuff with ReLU, so if you want to account for that, you have to correct for that somehow as well. But this is kind of in some ways, a more principled choice for keeping your Jacobians well behaved. All right, so the last topic I want to discuss in this part of the lecture, which is a little unrelated to this stuff, but I kind of didn't have anywhere else to put it, but it also has to do with gradients, is kind of the measure of last resort. What happens when it all goes wrong? So we would hope that if we initialize everything properly and we use batch norm and we normalize our inputs and so on, we'll get some reasonable behavior. Like for example, if we start off over here, we'll take the direction of steepest descent, and then maybe we bounce back and so on, and eventually we'll get to the optimum, right? Here's what might actually happen. You initialize, you take the direction of steepest descent, everything is fine, you think you're making good progress, and then bam, you get some monster gradient that just completely messes up your network, messes up the weight matrix, and because it took you so far away from where you were before, now you're maybe in a big plateau or in some other region where it's very difficult to make progress, and essentially your entire optimizer is done for. You're not going to make any more progress. Why might this happen? Well, because deep learning, right? So we're running a stochastic optimization with a very complex function class, maybe with a large data set, and that data set might itself be pretty messy, so there's a lot going on, and random stuff happens. Maybe we took a step that was too big in the wrong place, so maybe we're in a part of the loss landscape where there are really sharp gradients pointed in different directions, and we just took too big of a step, which catapulted us off into the wrong spot. Maybe something got divided by a small number, maybe in like batch norm or softmax, somewhere there was a division by some small quantity, leading to a really big quantity. Or maybe we just got really, really unlucky. Maybe we just got the worst possible combination of data points in our mini batch, and that resulted in a pathologically gigantic gradient. This kind of stuff just happens, and when it happens, you might see, for example, that your loss suddenly gets really big, goes to nan, goes to infinity, and then you're done. And usually, you end up with a positive feedback loop, because maybe initially you get a gradient that's just bigger than normal, but not actually infinite. Maybe it's like 1,000 times bigger than normal, but after you take a step with that gradient, now you're in an even worse spot, and now you have another gradient that's 1,000,000 times bigger than normal, and then you'll end up either underflowing or overflowing or getting a nan. So if you see that happening, perhaps the problem looks something like this. So there's a very simple solution that largely mitigates these problems, although you want to make sure that it's not due to a bug if you actually do get a nan. But if it's not due to a bug, then gradient clipping can often be a reasonable kind of band-aid to patch this issue. And there are basically two ways that you can clip your gradients. One way is you can clip every entry in the gradient so that it's no larger than some constant c and no smaller than negative c. Another thing you could do is you can clip the norm of the gradient. So it's just the difference between clipping every dimension or maintaining the direction and just clipping the length. Both of them are reasonable choices. It's kind of a matter of preference which one you use. And then the only real kind of choice that you have to make besides that is what to clip to, what to choose for C. Now, sometimes you have some intuition about your problem and you can just pick C manually. But if you don't, what you can do is you can run a few epochs of training, assuming it doesn't explode in those epochs. So run a few epochs of healthy training and just look at what healthy gradient magnitudes look like. Essentially, average together your gradients, plot their magnitude, or plot the average length of each dimension, and just see what those numbers look like, and pick C accordingly. You could choose it to be maybe like double that value, or something like that. So that can be a pretty decent way to choose C. Remember, you're not trying to do something really clever with C. It's really meant to be a measure of last resort for when something really blows up, and then you clip it a little bit. If you follow all the other rules, like using batch normalization and stuff like that, you shouldn't get these monster gradients too much, unless you have a bug. So choosing C somewhat heuristically is okay in that case.